Good morning, good afternoon, wherever you may be in your day. As always, thank you for choosing to make chemistry part of that day. And more excitedly, thank you for choosing to watch the Extra Problems Help. This is optional, and glad you're choosing to go above and beyond. So, let's get right to it. Alright, so here's a word problem. Again, how do we break down a word problem? Same way you eat an elephant, one bite at a time. So let's take a look at this problem. Your car's gas tank holds 18.6 gallons and is 1/4 full. You see a sign saying next gas station in 73 miles. Do you need to stop now, or can we wait to 73 miles if it's a 70-degree sunny day in New York? Okay, so a couple things here. Again, we want to go piece by piece and take a look at the data. My car, tank, that matters. The tank is 18.6 gallons. That's a piece of information. It's 1/4 full. That's a very important piece of information. You see a sign, whatever. Next gas station, 73 miles. That might matter. And the question is, do I need to stop? So we always want to know what we're answering. And then it's 70 degrees and it's sunny, and all of this is throwaway, and I added it intentionally because I wanted to put some throwaway in. And sometimes people ask, well, why do you give extra information? In real life, there's always extra information, and one of the key skills you can learn is how to distill out what matters. It doesn't even say I'm in New York. I don't care if it's sunny, rainy, cloudy. We're not talking. We're assuming that all these numbers are relative. And that's an important thing to point out too, and something I like to harp on is that all numbers have a little bit of wiggle room. That's the whole idea of the significant figures. So it's 18.4 to 18.8 gallons. It's 71 to 75 miles. Maybe the government does better. 72 to 74 miles. So things like wind drag and the how sunny or humid it's out. Those things are kind of taken into account in these types of problems. So we don't have to worry about it. Okay. So this is what I want you guys to get good at. Pull out the information that matters. Leave everything else behind. Make sure we're always aware of what we're trying to solve for. Always start with the end and work our way backwards. So, miles is a unit of distance. And if we're looking at our pieces of information, what's the closest thing to a length, a distance, or even miles itself? Well, yeah, it's the miles. Awesome. Why don't we start with that? Miles is on top, so we're going to put miles on top. And we'll go with an angry color. Sorry about that. And we get 16 miles per 1 gallon. And you can see we got the top done. Pat ourselves on the back. Good job, good job. We still got to work on the bottom. We have to get rid of gallons. Do you have any other pieces of information up here that deal with gallons? Sure. Gallons is a unit of volume, but we don't even have to worry about that because we have gallons itself. So gallons is on the bottom. To cancel it out, we're going to put it on top. And then my other unit is tank. So 18.6 gallons per 1 tank. And now I have miles per tank. Not miles. We still got to get rid of the tank. Do I have anything up here that deals with tanks? Sure, we have 1/4 of a tank. All right. If you want to write 1/4, that's fine. I'm going to put 2.25. And again, when we're given something with a problem, the other half of our mathematical equation is just a placeholder. It's not actually a number. It's not actually equal. But I do want you to get in the habit of putting those placeholders in. Now, if we look, we have miles on top, nothing, 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 nothing. So miles over 1, this is perfect. We punch it through our calculator, and I get 74.4 miles. Have we answered the question? Mostly, but not really. They asked, should we stop? And of course, the answer is yes. And why should we stop? Why indeed? If the sign is 73 miles, could it be 74? Could it be 72? Is 1/4 of a tank, that's like 1 sig fig, so we're really somewhere between getting 70 and 80 miles. So, of course you should stop. Stop the car, fill up and gas. You don't want to roll in on E. As Kermit the Frog once said in the Muppets, E is not, he said E meant enough. That's not quite right. It means empty. So, of course you should stop. And I like to point out this whole idea of numbers have wiggle room. So if we're really looking at this number is somewhere between 70 and 80 you can drive with your car. And that's a realistic look at what you can do with your car. All right. Does that make sense? Sure. 1/4 of a tank, 70 miles, drive for about an hour, drive for a couple hours on a full tank of gas. All that makes intuitive sense, and you should always ask yourself that at the end of a problem. All right. Let's take on another problem. And a full board. Because of the high heat and low humidity in Death Valley, California, a visitor requires about 1/4 of water every 2 miles traveled by foot. If the density of water is 0.99 kilograms per liter, at 45 degrees Celsius, a typical temperature in Death Valley, how many kilograms of water are required to walk 30 kilometers in 45 degrees Celsius weather in Death Valley? And as promised, English to metric conversion, English to metric conversion. So those are given to you. All right. This is a lot more typical of the problems you see in your book, and this actually comes out of an old Gen Chem book that we used in the past. Okay. Because of the high heat and low humidity of Death Valley, California, a visitor. Does any of that matter for the math? If you're saying no, good. What purpose does it serve? We are now excited to do the problem because it has real-world application. So now that we're properly excited to do math and chemistry, really it's math here, there's very little chemistry, but excited to do some science, we can ignore it. So let's just get rid of all this. Okay. We do need 1/4 of water for every 2 miles. Okay. Quart of water, sorry, not quarter, quart, 2 miles. And you can see that's going to become one of our qualities. Every 2 miles by foot, quart of water. Every quart of water, 2 miles by foot. Density of water. So there's a unit. And when you see these per signs, that's going to become our equal, right? That many kilograms per every 1 liter. So that's going to become our, our fake equal signs, but our top and bottom divider for the railroad tracks. 45 degrees Celsius, maybe that's useful, maybe not. And then it wants to know how many kilograms. So that is very important. And we want to walk 30 kilometers. That matters. We're in Death Valley, of course we are. And our 2 conversion factors are important as well that were given to us. So these are our pieces of information. So once again, if we pull out the stuff that matters and we get rid of this, what could be a very intimidating board. Hopefully it's not, but what could be an intimidating board? Oh, we filled every inch of it with words and numbers. I know. So let's remove that. And now we get this nice, calm, peaceful sea of numbers to work with. A quart every 2 miles. 0.99 kilograms in every liter. We want to know how many kilograms. We're going to walk 30 kilometers. We have 2 conversion factors. We know we're looking for kilograms at the end, and we have the railroad track all set up, and we can go manifest destiny all the way to the West Coast if we have to. We won't have to, but we might. Okay, so we're set up. Kilograms, of course, is a unit of mass. And what up here is another unit of mass, or even better yet, kilograms. The kilograms. So kilograms here is on top, so let's put this on top. Again, logic puzzle. And then the 1 liter goes on the other side. So we've done pretty good. We got the top done already. Pat yourself in the back. Good job. We're halfway done with this problem. All right. We got to get rid of liters on the bottom. We use this. Do we have anything up here that liters is a unit of? Volume. Good. Do we have anything up here that's a unit of volume? Sure we do. Quarts. That's a volume. Miles is not. Kilometers is not. Meters, miles, no, no, no. Now, quart and liters, do we have a conversion factor for that? Yes, it was given to us. It's over here. So we're going to use this next. So whether you pulled this to the side or you realize that you have to look up a conversion factor, that's a volume. That's a volume. We need a conversion factor. Heck, you can Google it, and if you say quarts to liters, and it'll put a number like this right at the top of the page. So liters is on bottom, liters on top, quart on bottom. And notice I left the numbers out. Make sure the units are right, and then we'll put in the numbers. So now we have kilograms per quart. So we still got to get rid of quarts. But we can use our number here now. 1 quart. Again, bottom, top. 2 miles. We're getting closer. Kilograms per mile. And so this is a unit of length. Do we have any other units of length? Yes. Okay. But that's kilometers and that's miles. Is that metric? No, well, I mean, that's metric, but that's English, so we need another one of those conversion factors. Dr. Wergo said he'd always give us one. Maybe it's here. Awesome. And we already have miles, so that's great. Miles is on bottom, mile on top, and for those of you that ran track and field, you may remember 4 laps of the 400-meter track will give you a mile. Close. And if you notice, there's 2 little lines at the starting line, a little curved one behind it, about 9 meters back. That's your conversion from the metric mile to the mile. So that gives us kilograms per meter. We need kilometers. So that is metric system. We can do that. 1,000 meters in a kilometer. And lastly, we can use our 30 kilometers. And voila, we have answered the question. If we punch this all the way through, we get 8.7 kilograms of water needed. And does that make sense? Boy, that's a lot of water. That's like, what, 20 pounds? Maybe not. 17 pounds? 18 pounds. That's a lot of water. Is that reasonable? So 30 kilometers, that's a pretty long walk in Death Valley. Could we really need 20 pounds of water? Sure, that's somewhat reasonable. I think that answer could be right. I'm going to hope it is. It is. And we're done with the problem. Thank you so much for your time. I hope this was helpful, and I look forward to working problems with you in class.